to render the 3D perspective on the sphere, I draw this equatorial plane. So this looks like a sphere. It's like a ball. And if I were to take an axis of rotation, now this does not represent a state, but an axis of rotation which is along the y-axis, it does not qualify as a proper NOT gate. However, if I chose my axis of rotation to be the x-axis, something that's pointing towards you, this does qualify as a proper quantum NOT gate. And if I have a state, suppose I had a state that is lying in this direction. This state is represented by ket 0 plus iota ket 1 under root 2. Alright? Now the question is that if the blue axis is my axis of rotation. Okay, first of all, let's look at this input state. Let's call it psi 1. So now I have a quantum circuit in which there is a quantum NOT gate, and I feed inside the circuit a state, which means a qubit comes in which is in this particular state, and the quantum NOT gate transforms the state. So I get an output state. This is what happens in any logic gate. You have information coming in, you process it, and you give an output. So what should ideally, forget about the Bloch sphere picture, what should ideally be the output for this state? Alright, if I had an iota here, if this were my input state, what should be the output? So 1 over under root 2, nothing happens to this. What happens to ket 0? It becomes ket 1. So I just write this like this. What happens to ket 1? It becomes ket 0, and there's an iota sign with it. So iota ket 0. So this is my intended output, my desired output from an ideal quantum NOT gate. Correct? Now there is no calculus in this. This is simple algebra, simple conceptual thinking. Alright? Does it make sense? Now let's look at the Bloch sphere representation of this operation. So the blue axis is my axis of rotation. Let me redraw the Bloch sphere, and as promised, I'm going to draw it in yellow all the time. This is my initial state. 1 over under root 2, 0 plus iota I. Alright? So it lies on the y-axis of this Bloch sphere. Now don't take x and y to be literal. And I've already claimed that my axis of rotation for a quantum NOT gate is along the x-axis. Now, could you please come to the blackboard? And could you describe to our class how this state is going to transform under a rotation of 180 degrees about this axis? Right, what's this? Alright. This is your state. Okay, good. Yeah, okay, consider anti-clockwise. Excellent. So, this state which is over here, if I consider the rotations to be anti-clockwise, this is my axis of rotation. I'm going to rotate, this is my object which is rotating, which is the quantum state. So nothing happens to the axis of rotation, it defines my sense of rotation. So I go up, the state goes up in the northern hemisphere on the north pole, and then goes back like this onto the minus y-axis. So if I do a 180 degree rotation about this axis of rotation, I will achieve a gate. Okay. Now we would like to see whether it has achieved the desired effect, whether the NOT gate has actually worked. This is what I would like to observe. So this state goes up like this, it moves like this, comes here and ends over here. So this is my final state as a result of this operation. Now what is this state quantum mechanically? What is this point corresponding to it? So this is a point on the Bloch sphere. So I would like to find out what this state is on the Bloch picture. Now how do I do that? So let's call this state, let's call it some phi. Okay, phi is a label, psi, phi, anything, this is a label. I'm just putting these in caps because these represent quantum states. So if I look at this state, phi, I know that a general state is given by cosine theta by 2 ket 0 plus Ei phi sine theta by 2 ket 1. Now what is, for this particular state, what is theta? Okay, let's not call it phi because I've used the phi here. Let's call it something else. Let's call it chi, something else. Now what is theta on for this state? What's theta? Right, so what is theta for this particular state? 90 degrees. So this is 90 over 2 is 45, cosine of 45 is 1 over under root 2, ket 0 plus. Now what is phi for this state? It's 180 because this is phi 0, phi 90 on the tutorial thing, phi 180, this is phi 270 degrees. So this is actually 270 degrees. Okay, so it's Ei 3 pi by 2. And what's theta again? It's 90. So I get 1 over under root 2. Now what's E raised to I 3 pi by 2? It's minus iota. What's E raised by? It's minus iota. So this is my chi over under root 2. But what is my desired output? This is my desired output. So this is my actual output that comes out of the rotation through an angle of 180 degrees about an axis that is along the x-axis. But my desired output, let me rewrite the desired output. Let's call it psi desired is 1 over under root 2 iota 0 plus 1 over under root 2 iota 1. Now is the desired output the same as the actual output? They are different. They appear to be different. So my claim that the NOT gate is achieved by a rotation about the x-axis seems flawed. It seems improper. But I would like to tell you that this state is just like this state. They are the same. Why are the same? Let me prove this. If I look at this state, or let's look at this state. Okay, I can start with this state and prove that this is equal to this state, or I can start with this state and prove that it's equal to this state. So let me start with this state and prove that it's equal to this state. So what I would like to do, I would like to take an iota out of the common. I would like to factorize iota. So iota goes out, this becomes 1 over under root 2, 0. What should I put here? Can you please indicate what should I put here? 1 iota or minus iota? Minus iota. Now this part is actually the same as this part. Iota into minus iota is plus. So I take iota out as a common. I get 1 over root 2 here. If I multiply this iota with minus iota, what do I get? Minus iota square, which is plus 1, and this is what I need. Alright? Now this state, chi, is the same as the desired state with this factor iota. Alright? So this thing equals iota times the desired state. So the question is, I would like to argue whether chi is the same as iota times the desired state. It doesn't look like the same because there's an additional factor of iota that is coming up. Alright? Now what I would like to write this iota as E I pi by 2. I can write iota as E I pi by 2 psi desired. Now what is happening here is that there is a quantum state, and along with the quantum state there is an e raised to iota factor with it. This object is a phase. It's a phase. And this phase factor is with the entire state. So this kind of phase is called global phase. And what I would like to argue is that if I have a state psi and I have a state ei some factor theta with psi, then this state gives you the same physics as this state. They are in this. It's not able to discriminate between these states or differentiate between these states in a physical experiment. They're just the same. Let me give you a motivation for this. Suppose I have a beam splitter and some input comes in. Let's say the input that comes in is psi. And the beam splitter has a property that it gives you two output beams. One is labeled, channel is labeled ket 0, and one output channel is labeled ket 1. And I have detectors at the end. I have a detector here, some D1, and I have a detector here. Now, what this beam splitter does, now I'm defining the action of the beam splitter. Let me finish my argument. I'm defining the action of the beam splitter. What this beam splitter does is that it takes an input state and gives you two possible outputs. One output is ket 0, the other output is ket 1. So it is projecting the input state onto either of the two basis states, which means that the probability that this detector is going to click is going to be the overlap of the state psi with this output state 0 modulus square. Okay? And this probability that this detector is going to click is going to be the input state projected onto ket 1, which is the overlap of the input state with the desired state, with the output state, modulus square. So I can calculate these probabilities. Alright? Now suppose I have another experiment. In which my input state, instead of being psi, is this state. That is, it has a global phase affixed to it. Now I would like to find out the probabilities of the two detectors clicking. So I have the same arrangement. D1 and another detector here, D2. And the human being who is making a measurement is after the two detectors. He has the two detectors in access, and he's looking at the outputs of the two detectors and is firing in many copies of a particle, each with a state psi or ei, theta psi, and is looking at the outcome. He's looking at the probabilities. आपको समझ आ रही? आपको कुछ खामोश से हैं? समझ आ रही? All right. So now I would like to find out the probability that this detector is going to click. Now, if I write down use the same formula, I would have ei theta psi overlap with 0. Instead of psi, I now have ei theta psi modulus squared. Now let's look at this function. Let's look at this overlap. Let's calculate this probability. Now, is this a number? Is this a number, a complex number, or is it a real number? Modulus squared is a real number, but this overlap itself can be complex. But it's not a quantum state, it's a dot product, it's an overlap, it's a number. Could be a complex number. Now, if I have a complex number A, I would like to find the modulus square of it. How would I find it? I would take the conjugate of A and multiply it with the number itself. Now this means, what I would like to do, now since this is a number, ei theta is a number itself, this object is equal to, I can take ei theta out of this bracket. It's just a scalar, it's just a constant. Okay, it's not a state, it's just a number. So I can write this thing as this, ei theta so I can just bring this out here. In classical sense, if I have a vector A, I have a vector B, but B is being multiplied by some scalar C. So I have a dot product between a vector and a vector that is being multiplied by a scalar. I can just bring the scalar out here. I can just take the dot product of A and B and multiply this with the scalar. Correct? That's what I've done over here. This is a vector. This is a vector, although in the quantum space it's not a normal vector, it's a Bloch vector, or it's a quantum state. I'm just taking this number out of this dot product or overlap. Okay? Now if I look at this factor, this is a number, I would like to find the modulus square of this number, so I'd like to find the modulus square of this and the modulus square of this. So now what's the modulus square of ei theta? It's just 1, because this is E minus I theta, the complex conjugate of this multiplied by the number itself. And I would like to find this probability. Alright? Now this is just 1, which means it doesn't appear in the final probability. the factor of ei theta in this input state does not appear in this probability. This output, the measurement outcome probabilities are the same in this experiment as they are in this experiment. So if I change an input state with the global phase factor, it's inconsequential. It does not show up in my measurement outcomes. So global phases, in 99% of the cases, they don't matter. However, keep in mind that this factor is also a phase factor here in this qubit, but it's not a global phase factor. So this is important. It's a relative phase factor between the two basis states. It cannot be factored out and written in front of the entire state. So it's not a global phase factor. This is important. This does have consequences. But a global phase is inconsequential. In most of the cases, it's immaterial. Alright? Now you had a question. This thing? This thing? So do you understand this? So it's a simple. It's ei pi by 2 is cosine pi by 2 plus iota sine pi by 2. So this thing is 0. This thing is 1. Okay. Alright. Any questions? Now let's talk a little bit about quantum interference. We've talked a lot about interference, but let me bring interference into the picture now for a quantum computer. Now I've drawn a quantum circuit or a quantum network. A qubit comes in, right? So this is an example of a quantum circuit. A qubit comes in onto this line. It sees a transformation. In our case, we're talking about a Hadamard gate. The qubit goes out in a particular state, and there's another Hadamard gate, a second Hadamard gate, and then a final output state. And we would like to find out the truth table for the Hadamard gate. We've already defined the truth table in our previous lectures that the Hadamard gate has the following property. And if the input is get 0, it produces an output which is a superposition. Alright? So this is my output from a Hadamard gate, and this is my input from a Hadamard gate. If my input is get 1, my output is 1 over under root 2, 0, minus 1. Alright? So this is how I am defining the operation of the Hadamard gate. एक मिनट पहले खामोशी हो रही एक मिनट Anything else? So this is the operation of a Hadamard gate. Now what is happening here is this circuit that I've drawn does not refer to any physical implementation. I'm not saying whether this is a beam splitter or what kind of physical apparatus this is. This is just a generic language for a quantum network. Okay? It's a physically independent diagram. It's like a flow chart. Okay? Or an algorithm for a quantum computing operation. Now some input comes in, it sees this logic gate, quantum logic gate, which is a Hadamard gate. Some output comes in here, then another Hadamard gate and an output. And in the previous lecture we saw that if my input is get 0, At this particular point, I would get this state because this is my input. And at this particular output, if the Hadamard gate once again acts on this state, I would get certain output. What would that output be? Speak up. Get 0. Alright? So now this is a generic diagram and we can implement this physically. Now how did we implement this? What we had, we took our qubit to be the path of a photon. Okay? So this represents the state of a qubit. This is the state of a qubit in this location. This is the state of the qubit after the second Hadamard gate. What is the qubit? It has to be physically implemented. If you want to build a hardware for a quantum computer, you have to choose your qubit. And you have to choose how are you going to implement the Hadamard gates. Right? So the software, the computer scientist will stop here. He will give you the circuit, the diagram, the flow chart, or the quantum network. He will draw these pretty straight lines and nice boxes for a Hadamard gate, and that's all what he will do. But now comes the physicist. He has to build it. So how will he build it? He will have to choose a particular physical picture of a qubit, a realization of the qubit, and a realization of the Hadamard gate. So one possible realization is that I choose the path of a photon to be my qubit. Which path is the photon taking? So this is the picture that I drew in the previous lectures. I have a beam splitter, and I have two of them, and I had a mirror here and a mirror here. And I have input photon coming in. I call this path ket 0, and I call this path output path ket 0, and I call this output path ket 1. So this is my qubit. My qubit is the path of a photon, and there are two possible paths. So it's a qubit, it's a two-level system, and there are two basis states. One is labeled ket 0, one is labeled ket 1. So now I'm going to physically implement this simple quantum computer, which is using quantum states to encode information, and our information is encoded in zeros and ones, but it's labeled, these labels go inside ket. So these are quantum states that are encoding quantum information. So now these photons, they change their direction because of these reflecting mirrors. Something happens here, and then the output, what we observe is, if we have two detectors, one of them is labeled path 0 and one of them is on the channel labeled path 1, only one of the detectors is going to click with 100% probability. Okay, so this is a physical picture of this quantum circuit. It's a physical realization. So this is hardware. You build a beam splitter. You design a beam splitter. An engineer can help you in that. But a beam splitter is designed that implements this operation, which a computer scientist has given to you, or a quantum computer scientist has given to you. So this is a physical picture, and the qubit here is realized by the path of a photon. Now the question is, what's happening here? A quantum state comes in, a superposition is created here. 0 plus 1 is created here, and the two paths then interfere. There's quantum interference between the paths such that only one of these channels is populated. Only a photon can come here. So constructive interference happens in this channel, and destructive interference of these quantum probabilities or states happens in this channel. And this detector will never show up. It will never give you a signal. So this is totally strange because this is a random device. If you just had one photon coming in, there's a 50% probability it goes here, 50% probability goes here. And if you just look at this beam splitter on its own, there's a 50% probability that it goes here and a 50% probability that it goes here. But when you put the two together and you don't have the courage to see in between, you just look at the final output, you get a result that is totally counterintuitive. You have two random devices giving you 50% probability and you're putting them together, and at the end you just see one. It's not acting like a random device. This combination of two random devices is not acting like a random device. It's acting like a deterministic, definite device. It's only giving you one output. So you have 2 coins, each one of them is giving you a heads or a tail, and at the end when you look at the final output, you're just getting heads. This is strange, but it is explicable, it is explainable by this language, that a superposition is created, and out of the two paths, one of the paths destructively interferes. Now let's try to, what if I would like to have this channel fired? So here you have brightness, here you have darkness. My little heart desires that I would like to have brightness here and darkness here. I would like this channel to fire. I would like this detector to light up. So what would I do for that purpose is, I would have to change, add another transformation inside this system. And what I would like to do is, I would like to modify this circuit a little bit. Let's first talk about the circuit, irrespective of the physical implementation. I would like to change this circuit a little bit. And what I would do is, that I would take the Hadamard. Remember that this beam splitter is now affecting or materializing a Hadamard gate. Excuse me, phone usage is not allowed in the class. Pay attention to this thing. So this is a Hadamard gate. It's physically implemented by a beam splitter in this particular case. Now what I do, I put another gate in between. Let's label this gate by P. P stands for a phase gate. Okay? So now, in between the two Hadamard gates, I put in another quantum gate. Remember, these are quantum gates now. They are acting on quantum states. This gate, let's call it a phase gate. I will need to define what this gate does. What is the transformation or truth table for this phase gate? So if I write down the truth table, now I'm defining the truth table. Input. So I only need to define what happens to ket 0 and ket 1, because these two states span the entire basis. They are all there is to be known. And I define the output of the phase gate. So this is the truth table for a phase gate. So if my input is 0, my output is 0. It does nothing to the input 0. I'm defining it in this fashion. And if my input is 1, my output is EI sum phi 1, where phi is a real number. Phi is a real number, EI phi is a complex number. This is my truth table. Now what's going to happen is that if I have this quantum circuit, if my input is 0, let's walk through the circuit. What's going to happen to the quantum state as it propagates or walks through the quantum network? So I start with ket 0. Now I first see the first Hadamard gate. What do I get? I get the superposition. Alright? So this is the quantum state that I have over here. This is my state over here. Okay? And I'm not observing it as yet. Remember this. Because observation or measurement destroys the state. It creates a new state. It collapses the state. I'm not making an observation. I've just put these elements together and waiting for the final results to appear in my detectors at the end. Just look at the nature of quantum information. You don't want to disturb the experiment because putting in a detection apparatus in between the apparatus is going to change everything. Okay, it's going to break the interference. Interference will not show up. The uncertainty principle is at work. So now we would like to see what's going to happen at the next stage. Phase gate. So now this state is fed into the phase gate. What's the output? 1 over root 2. What's going to happen to this state? Nothing. What's going to happen to this state? It's going to pick up a phase factor. Okay? Simple. This phase factor is picked up. Now we would feed this state is what exists over here. Okay. Now we would like to question. If I had my detectors placed over here, I didn't have the second Hadamard. What's the output that I get? 0. One half. And what's the output that I will get 1? It's again 1 half. Alright? Now this is an important point, by the way. I just breezed through it, but it's important. Now what I would like to do, I would like to feed this state into the second Hadamard gate, which gives me an interesting outcome. Now what's going to happen is that this 1 over root 2 factor remains what it is. Ket 0 is now transformed once again by the Hadamard gate into 0 plus 1. And then this is a phase factor. This is just a number, it's not a vector. So this just appears, just comes along for a ride. It just rides along. And now this state, this quantum state, will see the Hadamard gate as well. And the truth table is that it will produce this state. So I will get 1 over root 2 Ket 0 minus, I just put this factor in again, EI 5, 1 over root 2, 1. So this is my output state from this quantum network. Now let's find out the probabilities. If I place 2 detectors, if I have 2 detectors placed here, one of them overlaps onto the Ket 0 channel, the other one overlaps onto the Ket 1 channel, I would like to find out the probabilities. But let's simplify this state a little bit. Something entirely interesting is happening here. It's so fascinating. So the output quantum state, let me factor out, multiply out the 1 over root 2's, I get 1 half. Alright, so what I'm trying to do now, I'm going to write this as a superposition of 0 and 1. It's a qubit, so it's always a superposition of 0 and 1 with some complex numbers over here. So I take this state, I look at this factor, and I look at this factor. I just factorize out Ket 0 and I take this factor and I take this factor. So I get 1 plus EI 5. Correct? Correct? Is this correct? And here I would get 1 minus EI 5. Alright? Now let's talk about probabilities in a while, but let's physically implement this first. In the circuit that I've drawn on the top right, only one thing changes. I need to introduce a phase gate. The rest remains the same. So how do I introduce the phase gate? I take the same circuit, physical implemented by the path of a photon, by the way, these mirrors have nothing to do with the concept, they're just changing the path of the photon so that I can get interference over here. Nothing else. And I have two detectors. These wiggly lines represent the circuit lines that are coming out from these detectors. So this is the same circuit as I've drawn before. This is the first Hadamard gate implemented, the second Hadamard gate. Now I need a phase gate in between. So a phase gate can, so this is my ket 0 part, this is my ket 1 part. A phase gate can be physically implemented by putting some medium, some say piece of glass, or some other carefully designed medium in one of the parts, in one of the arms of the interferometer. What this does is that it gives a phase to a particular part, because it has a certain refractive index. It has a certain refractive index. When light comes in, it slows down, and that gives you a phase difference, because Kz is going to change. K depends upon the refractive index. But that's immaterial for the time being. You don't need to know all of this. But if I put a certain element like glass or some other crystal in one of the arms of the interferometer, it's going to implement a phase gate. Yes? So, there are different kinds of beam splitters. Physically, they are generally made of quartz, which is silicon dioxide, and two pieces of quartz, two prisms, equilateral prisms of quartz. They are joined together by some adhesive.
So how is this independent of the angle of incidence?
It does depend upon the angle.
Sir, then if it does depend on that, and if it does have a physical angle, and if it does have a refractive index, then how can we actually ignore the fact that we don't actually need to work out the probability, considering the fact that if it falls on the physical angle, or if it falls at an angle greater than the physical angle, we will have the reflection of our desired result.
Right. So you have to, you see, the pictures that I've drawn, the nice quantum diagrams that I've drawn, they're independent of the physics. But once you start building a quantum computer, you have to take all of these factors into account. You have to have a properly designed beam splitter. You have to have the alignment of these optical beams precisely tuned. So everything has to be engineered so that it matches the description of all of these components. So this is the art of experimental physics.
So that is how basically we decide at what angle it should fall that.
Right. So this is something that you do in the laboratory. But these are important points that an experimenter has to pay attention to. Alright, now, so this is how this, let me finish, this is how this circuit, which I've drawn with the phase gate, can be physically implemented. Now I would like to find out the probability that this detector D1 clicks. Let's call this path 0. Can you please calculate, I give you 5 minutes for this. Can you please calculate the probability that this detector is going to click given this is our state? Just looks frightening, but it's actually quite simple. Don't be frightened. Don't be frightened. Please start the calculation. What? Huh? Sorry? अब क्या कह रहे हैं? ओके, थोड़ा सा पहले ये कर लें फिर ताकि आपका सवाल सब सुन सकें. पहले कैलकुलेशन कर लें. Remember, I would like to take the overlap of that quantum state with ket 0 and find the modulus square of it. Of course the output, that's what you're observing. So human beings enter into the picture over here. They set it up and then let quantum mechanics run its course, and then you see an output. Just destroyed, but interference determines which detector. Well, which detector is going to be detected in So you want to find out that this detector clicks. So you need to find the quantum state here. The quantum state here is given by this. It's overlapped with this state. This is fine. This result is the result. So one student has come up with the correct answer. I don't want you to give me a correct answer. I would like to see an effort here. Yes, simplify it further. Write in terms of cosine and sine. No, it depends upon the time. Good. Can we simplify this further? Write this as sine or cosine. Excellent. Some students have indeed. So I think you're on the right track. Good. So let me do this calculation for you. So I take this state, psi out, and find the overlap of this state with this state. Okay, because I want to find the probability that this detector is going to click. So this becomes 0, modulus squared. That's it. So now what's the overlap of this quantum state with ket 0? It's just this factor over here. Because the overlap of this factor with 0 is 0, because 0 is orthogonal to 1. So this is the probability amplitude. Okay, so this becomes 1/2 1 plus E I phi modulus squared. Right. So this final two detection scheme is just picking up one of the coefficients. Alright. Now I could find out this probability, I can solve this. The probability that detector D1 clicks is, now this is 1/4. I would like to take the complex conjugate of this, which is 1 plus E minus I phi. Then I multiply this with the number itself. That's it. Now it appears that these complex numbers are appearing in a probability. It's incorrect because probabilities are real and they're non-zero. But let's work it out. Let's simplify this further. The complex numbers are not harming us. They are a convenient mathematical tool. The probabilities are all turning out to be real. So this is 1/4. 2 plus 2 EI phi plus 2 E minus I phi. Let me do the complete calculation. Only once, I'm going to do it only once. So what's the product of multiplying this with this? 1. Okay? Now what is this object equal to? Now this is a complex number added to another complex number which is its conjugate. It gives me a real number. And this turns out to be 2 cosine phi. Now you will have to remember things of this minor nature. You don't remember, these become your second habit if you do enough of physics and math. So this becomes 1/4 2 plus 2 cosine phi. This becomes 1/2 1 plus cosine phi. Can I simplify this a bit further? I can write this as cosine square π/2. So this is the probability that detector D1 is going to click. Yes. Why can't I take the modulus square of this? Right, the question is, why do I have to take this overlap? So I have a quantum state here, which is given by this. I would like to find out the probability that one of the detectors clicks. Okay, so I take the overlap of the quantum state with my output state, with the state that is actually active on this channel. So it's like a vector. The vector is projected onto my measurement axis. My measurement axis is kept 0, and if a vector pointing in an arbitrary direction, I find its projection onto ket 0. That's what I'm doing here. Alright? So this is the final result. It depends upon phi. So now I can change phi. If I were to make a plot between phi and the probability that the first detector clicks, What is this plot going to look like? It's going to look like a cosine square function. Always positive or zero, non-negative. Which makes sense. Real number. It's going to look like this. And remember, when we looked at the double slit interference pattern, we exactly get a cosine square of some factor. It's exactly interference that's happening here. And if I look at the other detector, the probability that the other detector clicks. Suppose I would like to find the probability that this detector clicks. Can you immediately tell me what the answer is going to be? 0? It's going to be sine square phi by 2. So that probability is going to be look like this. And in any one phi, the two probabilities add up to give you 1. Let's take a 10-minute break.